Hi everyone, today we've got our chapter 14 video, which is all about the rules of probability. In chapter 13, we saw cases where we had very specific situations where events were independent or disjoint. What we're going to see today are probability rules that apply to every situation, whether events are disjoint, independent, or not. If you recall in chapter 13, I talked about a special situation where if we talked about two events, A and B, and we wanted the probability of A or B to happen, then if they were disjoint, meaning they could not happen at the same time, then the probability of A or B happening was just taking the probability of A and adding the probability of B. Well, oftentimes, and actually most of the time in probability, events are not going to be disjoint. Typically, two events are able to happen at the same time, and this equation will not work for that. So what I'm about to show you is what we call the general addition rule, which means that it works even if two events aren't disjoint. So when it comes to any two events, whether they're disjoint or not, the probability of A or B, we're going to take the probability of A plus the probability of B, but then we also have to subtract the probability of A and B. So here, we're not just taking the probability of A and B and adding them together. If it's the case that two events are not disjoint, there's going to be some small overlap between the two events. So by adding A and B together, we actually add that middle section twice, which is why we have to subtract the probability of A or B. And in a moment here, I'm going to show you how this is popping up in a Venn diagram form. So before I dive into this, I'll remind you that probability of A or B is much more inclusive than probability of A and B. For A and B, it has to be both of them, where probability of A or B would be included in that probability. So in the general addition rule, where we talk about probability of A or B, you might be wondering, why do we have to subtract that probability of A and B? So we take the probability of A plus the probability of B, but then we subtract the intersection, the probability of A and B. Well, looking at this Venn diagram, take a moment and see if you can figure out why we have to subtract that middle piece of A and B. Okay, well, hopefully you took some time to think about that. So why do we have to subtract this middle A and B part? Well, if we're taking probability of A plus the probability of B, let's see what happens when the two events are not disjoint. In other words, there's some overlap because they can happen at the same time. So if we take probability of A, that is this section right here that I'm circling in green. Then if we add the probability of B, that is this pink section right here, probability of B. And if you look here, we actually circled the section in the middle, probability of A and B, twice in this case. So when we're looking for the probability of A or B, and there is an overlap between the two events, we cannot have it where we don't subtract the middle portion. In other words, we can't count that twice. So that's why when we do A, then add B, we actually find that intersection twice. So when it comes to that general equation for addition, that is why we have to subtract the middle piece. So here, if we add probability of A and probability of B, we will count the middle section twice, which means we have to subtract one of them. So here is a quick example of when we might use that general addition rule. So in this example, we're actually going to talk about pets. If you think about pets, you can have a cat, but you can also have a dog, you can also have a cow, you can have numerous types of animals, right? So in this case, there might be a situation where two events are not disjoint. In other words, they can happen at the same time. So for our purposes, let's say that the probability of somebody having a pet fish is 0.5. Then the probability of having a lizard is 0.3. And then the probability of having both a fish and a lizard is 0.1. We want to use that general addition rule to figure out what the probability of having a fish or a lizard is, okay? Well, using that general addition rule, we want to know what the probability of having a fish or a lizard is. So we're going to take probability of fish plus probability of lizard and subtract probability of both. In other words, 0.5 plus 0.3 and subtract 0.1. which gives us an overall probability of 0.7. The key thing here that I really encourage you to look for is the word or. So if you see the word or, you're probably going to jump over to this general addition rule and then make sure that you subtract that intersection. There's another type of probability that we're going to see quite often moving forward. And in fact, this conditional probability comes into play later on in the year, like second semester, way down the line. So it's really important that you understand the idea of a conditional probability. So when it comes to a conditional probability, we are interested in the likelihood of something happening given that another event has already happened. And this is exactly what we call a conditional probability. So given the condition that something has happened already, what is the probability of this other event happening? So in our notation, what we say, it looks like this: probability of B given A. So that vertical bar, that stands for given. So we want to find what is the probability of event B given that A has occurred. So if you are trying to find the probability that event B has happened, given that A already happened, we are going to use this formula. And this is a formula that's actually on your formula sheet, which I haven't given to you yet, but it will be on the AP exam. It will also be provided for quizzes and tests and everything. So if you want to know what is the probability of event B given that A has happened already, you want to take the probability of A and B on the top, and then you want to divide it by whatever is given, in this case, the probability of A. So if we look at this equation, obviously, because we're dividing by probability of A cannot be 0. And that kind of makes sense. Obviously, you can't divide by 0 ever, but in our definition of a conditional probability, we are saying that we want to know what is the probability of B given that A has happened. Well, if the probability of A is 0, that means it hasn't happened. So that's why this equation works. We are saying with certainty that probability or that event A has happened already. So one way to think about this, I know I've got a volleyball here. Maybe a few of you play volleyball. What if I ask just in general, what is the probability of being a volleyball player at Fargo North High School? So you might think about, well, if there's about 1,000 students, maybe 50 of them are in volleyball. So you could take 50 divided by 1,000 and say that is our probability of being a volleyball player. Well, in this case, if I said, given that someone is a female, what is the probability of them being a volleyball player? Well, I think we all would agree that that probability would then go up because all volleyball players in North Dakota are female. So that would lower our pool or our given probability. So given that they're female, what's the probability that they play volleyball? Well, that would be a much higher percentage than out of everyone at Fargo North. So here's another example of conditional probabilities using that prior example with pets. So again, the probability of having a pet fish is 0.5. And we could say that the probability of having a pet lizard is 0.3, and probability of owning both is 0.1. We might want to know what is the probability of having a fish given that the person has a lizard already. So again, we know that the person has a lizard, and we want to know of the people who have lizards, what's the probability that they also have a fish? Well, our formula in this case, with our new notation, is going to be what is the probability of fish given that they have a lizard? So on the top, you see we have probability of fish and lizard, so the intersection of having both, and we are dividing by the probability of our given event, in this case, given that they have a lizard. So the top one, probability of having both, is 0.1, and then the probability of owning a lizard, our given, is 0.3. So altogether, given that someone owns a lizard, the probability of owning a fish is 0.333. So we talked about the general addition rule. It might also be helpful to talk about the general multiplication rule. In chapter 13, we saw that if two events A and B were independent, in other words, the outcome of one event did not influence the outcome of the other event, then the probability of A and B was the probability of A times the probability of B. But of course, we know that events are not independent most of the time. Typically, one event's outcome is going to influence the outcome of another. So just like with addition, it's going to be useful to have a general multiplication rule. So the general multiplication rule, the reason I talk about this after the conditional probability formula is because it actually comes exactly from that conditional probability formula. All you have to do is multiply or divide, switch some numbers around using one-step algebra 1 skills, and we get our probability of A and B formula. So the probability of A and B, there are two ways to think about this. It is the probability of A times the probability of B given A. Or if we flip that around, it can be probability of A and B is equal to the probability of B times the probability of A given B. So the main thing here is that this explicitly is not given to you on the formula sheet, but because the conditional probability formula is there, you can rearrange that in one step, and I'll show you that in class to get this exact formula. So now that we know more about probability, this is where we can get to a more rigorous definition of what it means for two events to be independent. Up to this point, we've basically said if two events don't influence the outcome of each other, then we consider them to be independent. With our knowledge of conditional probabilities, though, we can now mathematically show that two events are or are not independent from one another. So by definition, this is the definition you want to go to now. We say that two events A and B are independent whenever the probability of B given A is equal to the probability of B. In other words, another way to say that is given that B has happened, the probability of A is equal to just the probability of A. And we're going to see an example of this here in just a moment. So here's an example talking about different types of schools that we have in the US. So here's our problem. The probability of a randomly selected person going to college after high school is 0.76 in the US. So if we take any high schooler in the US, doesn't matter what kind of school they go to, 76% of them will go to college. Now, given that someone went to a private high school, the probability of them going to college after high school is 0.96. So out of just the private school people, that percentage goes up to 96%. We want to know, are the events going to college after high school and attending a private school independent events? Well, without even diving into the math, you can probably see here that these two events are likely not independent. We see that if you went to a private school, you are more likely to go to college than if you were just in the general population. But what we're going to see is mathematically how you can prove that these two events are not independent. So what we're looking for here essentially is we want to know, is the probability overall of going to college the exact same as the probability of going to college given that somebody went to a private school? And that is our definition of independence. If these two things are equal to each other, then they are independent. They have no influence on one another. But if they are not equal to each other, then we would say that they are not independent. In other words, they do influence each other. So we saw in that example, the probability of going to college overall is 0.76, while the probability of going to college given that you went to private school is 0.96. So again, we see you are more likely to go to college if you went to a private school than if you were from the general US population. So in this case, 0.76 is not equal to 0.96, so we can conclude that they are not independent events. In other words, you are more likely to go to college if you attended a private high school than if you were from the general population. We have just two really quick final concepts to talk about when it comes to probability. The first one, as you can see in the top right, we've got Harold playing cards with his good friend. It is the idea of drawing without replacement. So sampling without replacement, this means that once we select an individual, we do not put them back into that pool to be selected again. So the most common example is a deck of cards. If we're just selecting cards from that deck, take a card out, we do not put that card back in. That's an example of drawing without replacement. We could do the same thing with drawing names out of a hat or taking dollar bills out of a wallet, anything like that. That's an example of drawing without replacement. So if you think about a really large population, take the biggest population we know of, everyone on Earth, around 8 billion people. If we take just one person out of there and don't replace them, that really does not have a significant impact on our overall denominator and therefore probability. So when it comes to large populations, drawing without replacement doesn't really have much of an impact. But if we're talking about a small population, that definitely has an impact. So if we're talking about 52 cards, take one out, that's significantly going to change our denominator there. So for example, if we wanted to, in a standard deck of cards, which is 52, we might want to know what is the probability that the first two cards you draw are not hearts, but the third card is. So for the first card, we are drawing out of 52 cards, and we don't want the first one to be a heart, so that would be 39 out of 52 cards. But on the second card, again, we don't want that to be a heart, so we have now 51 cards, that would be our denominator, and 38 of those are not hearts. And then on the third card, we're now down to 50 cards, so that would be our denominator, and now we have 13, so 13 out of 50. To get our final probability, you would just multiply those three numbers. When we get into class and once we get rolling on this, I will show you guys an example of this. It really is pretty quick. The main thing though is that once we take a card, that's going to change our denominator, and then ultimately we are going to multiply numerous fractions together. So the final idea we have for probability is the idea of a tree diagram. It is just a really useful tool and diagram for us to use when we come to conditional probabilities or events that have numerous sequences to them. So we have one thing happening, then another thing happening after the fact. So they kind of look like branches of a tree. We start with 3 or 2 main events, and then we kind of branch off from there. So that's where the name of a tree diagram comes from. And like I said, they're going to become most useful in cases where we have conditional probabilities as well as numerous events happening at the same time. So a good example of this is number 48 from chapter 14's homework assignment. And that's actually how I'd like to start class when we get to class this week. So that's what we have for probability. You now have all of the foundational skills. You have the general rules for addition and multiplication. You've got a few diagrams to use, and you know about the idea of drawing without replacement. So in class, we will have some work time on this. Practice really does make perfect when it comes to probability. But if you'd like, in the meantime, to try out a few problems, that might not be a terrible idea.